Hello everyone. Today we're going to learn about linked list data structure. This tutorial is a part of the Data Structures and Algorithms class. This is the high-level visualization of a linked list data structure. When we say linked list, we're referring to a singly linked list. The linked lists contain a list of nodes that linked together in a linear order. You can have as many nodes as you want in the list. Each of the nodes contain the data. For example, this one containing data is the letter A, and this node is containing the data of the letter B, and this node is letter C. Each node is also pointing to the next node. In this case, A is pointing to B and B is pointing to C. These are the links. We have a list of nodes and we have links between them. That's why this data structure is called linked list. So this is how it looks like on high level. And on the right, you will see this is how it's roughly look like on your computer memory. Each of the big blocks here is one node. These are the physical addresses of the node on your computer memory. Node A has the address of 1, node B had the address of 23, and node C had the address as 18. This can be very random. Within a node, you can see that the node is holding the data, which is A for this node, and also the next pointer, which is holding the address of the next node. Node A's pointer is holding the address of node B, which is 23. And node B is holding data B, and the pointer of B is holding the address of node C, which is 18. Node C is holding data C, and it's not pointing anywhere because it's the end of the node. So the pointer value is null. So this is how linked list data structure roughly look like on your computer memory. This is how we implement linked list data structure in our code. First, we create node A with data A. If we print it out, we have node A with data A. Right now, node A is not pointing to anything. Then we create node B with data B. And if we print it out, we have node B, and it's not pointing to any node. To link two nodes together, we simply assign node A.next equal to node B. Then if we print node A out, we can see that node A data is A and the next pointer is holding the content of node B. But under the hood, next pointer is just holding the address of node B. This is called preferencing in JavaScript. And we will learn about the preferencing shortly. So that is linked list data structure on high level, on your computer memory, and on your code. We have another kind of linked list, which called doubly linked list. Doubly linked list is exactly the same with linked list with a small addition. That is, a node is also pointing to the node before it. So instead of one pointer, a node in doubly linked list has two pointers. The next pointer and the previous pointer. The next pointer is pointing to the node after it, and the previous pointer is pointing to the node before it. This previous pointer opens a new capability. That is, you can travel backward, so it's a two-way street, as opposed to singly linked list, which you can only travel one way. Next, we're gonna learn about shallow copy and deep copy in JavaScript. This is an important concept in JavaScript, or probably in any programming language. So in JavaScript, when you assign a new variable to an existing one, that means shallow copy. It's also known as preferencing. So what happens in your code is the two variables, the original one and the new one, are holding the same address to a memory space that contains the data. This picture helps to visualize that idea. We have an original variable containing the object with key A and value 1, 2, 3. On our computer memory, this is our data A, 1, 2, 3. And this is our original variable. When we assign a new variable called shallow copy equal to original, we're actually referencing the new variable shallow copy to the same memory space which is holding the object A123. Because these two variables are pointing to the same memory space, any changes you make on one variable will be reflected on the other variable. The data in the memory is the only source of truth. Referencing or shallow copy happen all the time when you're assigning a new variable to an existing variable. It helps to save a lot of memory space because, as you can see, no matter how many new variables assigning to original one, the cost of the memory space to host the data is always the same. And this is exactly what happened when we link two nodes together in the linked list. So the next value here is only holding the physical address of node B. When we print node A out, JavaScript simply knows the address of node B, fetch the data, and put it here. Going back to our shallow copy, we have a case when the original variable is reconstructed or reassigned to a totally new value. The shallow copy then will have its own copy of the data. We will see an example about this in a minute. So that's shallow copy. In reality, sometimes we need the new variable to have its own copy of the data, and that's called deep cloning. JavaScript doesn't have an official solution, but we can have a simple workaround by turning the original value into a string and then pass that string into JSON, combining these two steps to create a deep clone of the original data. Let's have a look at some hands-on coding of deep copy and shallow copy. First, we create an original object A123. Then we create a shallow copy of the original object. And we also create a deep copy of the original object. So if we print them out, all of them having the same data 1, 2, 3. If we modify the original object, in this case A is equal to 456. If we print them out, the original value is now 456. The shallow copy is referencing the same value, so it's also 456. The deep copy has its own copy of the original, so it stays 1, 2, 3. If we modify the shallow copy, in this case A is equal to 999, notice that the original object is also 999 because it's referencing to the same data of shallow copy, which is now is also 999. Deep copy has its own original copy, so it stays 1, 2, 3. Now if we completely reassign the original object or the shallow copy, the referencing is now broken. The original and the shallow copy will now has its own copy of the data. So the original object data is now B789 and the shallow copy object stay the same A999. The deep copy data doesn't change throughout the whole course, which is 1, 2, 3. Next, we're gonna build our linked list data structure. Notice that we will only have a variable head that's pointing to the first node, and tail is pointing to the last node. This is optional. First, we create a simple structure of the node. It's an object with two fields. Data is the data of the node, and next is a pointer that's gonna point to the next node. It's node by default. So this is how one node look like. Now we're gonna build linked list data structure. First, we initialize our linked list with no node, and we're gonna keep track of our linked list length. When we insert the new element to the linked list, we create a new node with that data. And if the linked list is empty, we can simply point the head to that node. And if the linked list is not empty, we will travel to the tail node and point the tail node to the newly created node. Then we increase the length of the node to 1. To delete a node, we check if the first node is the node to delete. If it is, we simply point the head to the node after the first node. If the first node is not the node to delete, we keep traveling from node to find it. And if we found it, we simply link the next pointer of the previous node to the next node. And then we decrease the length of the linked list to 1. To search a node, we simply travel from node to node. And if we found it, we return the node. So that's our linked list data structure. Then we're going to initialize a linked list data structure. And if we print it out, of course this is empty for now, with the length of 0. Next, we're going to do operations in our linked list data. To insert, we simply insert an element value. And if we print it out, we can see that head is now pointing to node A, and the linked list has length 1. If we insert another element, and we print it out, we can see that node A is now pointing to node B, and the length of the linked list is 2. If we delete, for example, node with data A, if we print it out, head is now pointing to node B. Before doing search operation, we can insert some more nodes, like C, D, and E. So if we search for E, E is now the end of the node. So then we're gonna have the node of E, and it's not pointing to any node, because tail node is not pointing to any node. If we search for F, F is not in our linked list, so it's gonna return no. Next, we're gonna briefly talk about doubly linked list. So the main difference between doubly linked list and singly linked list is, with doubly linked list, node to node travel is both ways. So you can go head to tail and tail to head. With singly linked list, node to node travel is one way. You can only go head to tail. And this is the visualization we see before. A can go to B and B can go to A. Same thing with B can go to C and C can go to B. Next, we always remember how fast to do operation on our data. For linked list and doubly linked list, we have O1 insert and delete at the head of the linked list, and ON insert and delete at random. For search operation, it always takes ON. There's no access operation in linked list. That's it for today's tutorial. Thank you for watching, and I will see you in the next video.